everyone. It's a really pleasure to be here. First of all, I would like to thank the organizer and the committee to allow me to share my work. I remember that last year it was my first CT2024, and now I was in the audience, and now I'm in front of you, so I will try to do my best to do good work as we had last year. This is the journal work with my supervisor, and since I come from UCLouvain, I will do some neighboring categories, of course. So my title is about non-additive derived functors, but what is for me an additive derived functors? It's the usual one. And here the slides about having categories, so just recall what is the main definition and well-known notion. So here, let's take F and additive functors between two main categories, C and E, and we ask in addition that C has an projective, then for the integers N, we can define so-called nth-left derived functor for F. And it's defined with this formula when we start with X and we can C, and then we use to apply F on the projective resolution of X, and then we compute the nth homology. It's very important that this assumption on C is not linked at all with the abelian assumption. It's just to guarantee that we can compute and have such C of X with just a chain complex which is exact everywhere, or the object is projective. In addition, the homology on degree 0 is C itself, and there are many examples of satisfy this condition. For instance, any variety of algebra satisfy this condition, and we have groups which is not abelian category and also abelian category, so this is not very abelian. Okay, so that is well known. And the important thing is why this is well defined. And this is well defined for three reasons. The first thing is that for one object, we can build several different projective resolutions, but they are unique up to homotopy. The choice of F is guaranteed that the homotopy here will be preserved. And finally, it's well known that if you are to be equivalent, then you will be isomorphic in homology. And that statement will allow us to consider derived functors. Okay, but that is for me the additive one. And that is well known, so if I just need my talk here, it will be okay, good for you because coffee break is now, but just no. But here, as you can see, everything I use here, the twist that the two first steps I use homotopy. And homotopy is defined in this way. So homotopy between two chain morphisms is defined with a collection of morphisms Hn satisfying such condition. As you can see, we need abelian categories for that makes sense because we need that the onsets are abelian groups. And so, how can I talk about non-additive derived functors? And here, everything we need additivity of category of functors, how we can do. And so that's the purpose of my talk, just to convince you that we can still apply this formula using the same idea here to prove that we can compute derived functor but outside abelian settings. And the first trick would be to rewrite this thing in this setting. The main thing is that we are now no more plus but only minus. Okay, for moments it makes no sense, but let's keep in mind that minus will be a key point here. My talk is divided into several sections. The first one is, okay, to have good subtraction minus operator. Then I will use it to build what we call approximate homotopy. Then, okay, this condition is strange for the moment, but keep it secret for the moment. Then I will have to take suitable functors, and then if I combine the fourth two, I will end up with what I call non-additive left derived functors. And I have to have time at the end to talk about some special approach and to compare with. Okay, so okay, I'm talking about non-additive, but what is for me non-additive? It's non-abelian, and my research led me to several notions. And the first one is the more general, is the notion of normal category, in the sense of derived, which is a point category, bar regular, and where all the regular morphisms are concurrent. Then a stronger one version is the homological category that we talk about today. And then, of course, what we love in quite enough is the categories, in the sense of Gialinese, Marquet. Just to avoid confusion here, I should mention that it's George and Gialinese, and the first one is George and Gialinese. And so here, as you can see, the stronger notions are in categories, but then if you go downwards, it's weaker. And here I have a couple of examples of having categories, so having groups, having categories, the algebra, groups, cosmodus, introduce the principle, multiplier category, we just had JK groups, and normal category, we had the example of pre-ordered groups studied by Clementino, Nelson Ferreira, and Montoli, if I'm not mistaken. Okay, so that will be our setting for today. But first, I need a mouse. And the idea is just to look what is in every category and see what we can do outside. Because I don't want to find another version which does not fit if I come back to the abelian case. So this is how we do a lot of vice versa between the abelian settings and the non-abelian settings. So in every category, the minus is encoded in this pictorial sequence. But the minus is just here in the kernel. Okay, so let's translate this in a point category with kernels and binary products. Here we don't have any more pictorial sequence, but we still compute the kernel of the co-diagonal. Dx will not be longer x. But we will just take dx as kernel. And then here we have the on top, these triangles encode the difference of f and j, two parallel morphisms. Then we just take the same definition. The only difference is that the domain is no longer x, but d of x. But this is a morphism, not category. Okay, this may be random approach, it's a good approach, in the sense that with this definition that I showed you before with my triangle, we recover good properties, such that the fact that the difference is like stable if we pre or post compose, and here d of L is just the restriction of this induced map to the kernels, because d is defined by kernels. And moreover, we have what we expect for difference. If you subtract two things, we want that they vanish. And that's true all the time, but if you want to have the converse, sorry, if you have two are the same, then they will vanish, if you just compute the difference. And if you want the converse, we need in addition that the category is normal in the sense that it's related. Great. Okay, this is still a bit a harder construction, but it was been studied a long time ago in the sense, or in the context of subtractive category. In the subtractive category is a pointed circular category with binary products, and it should be subtractive when all the morphisms of this shape, which is just 1 minus x, starting from here next to x, is a regular morphism. Okay. Just to clarify a bit, any homogeneous category with binary products is, in particular similar categories, will satisfy this definition and will be normal, so I will have all these settings above. Okay. Okay. It seems that I have my mouse, but I'm still a bit stuck. I need the homotopy. And so the idea is to see, is to come back to the abelian settings and hoping that we can build between two different projective resolution an homotopy to lead for the first bullet that I show you at the beginning. First, we need the lifting. So if you start with a morphism, we need that the lift to the resolution of x and y, and that is always true. And if you consider a point category of its kernels, that's always possible. But classically, this lifting is unique at homotopy. And so let's look what's happened in the classical abelian context. So let's take two lifting, f and j. So here f0, g0, f1, g1. Since both are lifting of x, this difference factor to the image, because I recall that here I have a projective resolution, so it is exact. So I factorize through the kernel of n for the image. And then since g0 is projected, and here I have a regular morphism, it's alpha 0 factor to here, and so this is my first map of my homotopy. Okay, that is done classically. This is a classical way for our categories, but I'm not in the abelian setting. So just the problem now is that my difference starts from d of c0, no longer c0. And I know that c0 is projective, but I don't know for d c0. But let's assume that for the moment that's all that d c0 will be projective, so I can use the same strategy and we can continue this procedure. This leads us to an homotopy that we call approximate homotopy between positively graded morphism, because I just built it for projective resolution, and again a collection of morphism Hn starting now from this domain, because when I iterate this condition, I go higher and higher with the d's, and end up with En-1. And this will satisfy this condition, which is, looks like the same as the event settings. And this one is a bit different, but here I just compute several times sigma, and sigma was my 1 minus 0, so in reality just 1, so the identity. And I have this correction term here. Okay, but what does it look like in the event settings? As we expect, as we know. Here it is valid because it is the identity. These are just the identity itself, because this defines the kernel of the co-diagonal, but it's just identity in the identity settings. Great, so I have a minus, I have an homotopy. Okay, but what about homology? Okay, but it seems also perfect. So we prove that if you consider very general settings, so normal category, just subtractive, then if you have an homotopy between two positively graded chain of morphism, then they will have the same homology for any degree. And that was one of the key goals of the proof for the abelian settings for derived functors. Okay, but
what is Hn?
Sorry?
What is Hn?
Hn, I built it here, so it's the same procedure. So it's my homotopy that I will build. So if you
so you don't need any additional condition. Okay, what is a chain complex?
So here I just cheated it. I need an extra condition. So what I did is try to copy paste this procedure. But here,
what you're saying is wrong, and wait.
I will correct it now because I'm really.
Okay, then it's okay.
This is my vague obscure condition. So yes. So yes, that's making a point. So I have a lifting, and this lifting is unique if all my d's of Cn are projective. That's my condition, is obscure and need. But what I know for the moment is that only the Cn are projective. And just recall that the difference is equal to this diagram. So x, let's say that x is projective. Okay. Then general statement, co-project will be again projective. And what I want to fit with this hope is that the d of x remain projective. Don't forget that in the abelian settings, this is just x, so that's probably satisfied. Okay, but I will ask.
You assume the x is projective
yes.
for all x?
Yes. No. So we can I'll start with an object x projective, then I will hope that this thing will be projective as well.
So you start with particular x and
because if you prefer, here I'm starting with a projective resolution. So here C0 is projective. And so I'm asking that D of C0 is projective as well. So D preserves projectivity somehow for the objects. It's better? But you can discuss it later. Okay, so I will just need this, but I will ask more than that. I will ask condition P, which is just for quantum category. I said a satisfying condition.
But you did not answer what is H sub x.
Sorry?
My previous question was what is H sub x?
Which one?
Yeah,
this is homology. This is homology. Homology of what? So it's the functor homology between.
Homology of what? Of chain complex?
Yes.
My question is what is chain complex?
Chain complexes.
It's true.
Just
okay.
Such that if you compose the two morphisms here, you have 0.
Okay, and then how will you define homology?
But we can discuss later on if you
the problem is why the image of D is a normal.
But homology is something it's defined.
Are you abelian categories?
No.
If it's a resolution, then it's exact, so the Linux is equivalent.
Yes.
If it's a resolution, then homology is used.
Yes, it's for doing text nice statement. I'm starting to working with projective resolution on top and below, but this is a statement for, I'm not assuming that I'm dealing anymore with projective resolution. I'm just taking this as a definition of homotopy, and then I prove that the homology is the same. I'm not talking about projective resolution. But I will continue with this.
So, if this is a chain complex of groups, why HN is well defined?
Sorry?
How will you define HN?
But as usual, as you keep in mind, but maybe I will prefer to.
Okay, you just define. Okay. Nice.
So that's sorry.
Sorry.
So I come back to this obscure condition. So what I want here is that P of x is positive is a type of x projective. But I will ask more than that. I will ask that if I have such a situation where K is a kernel of a split epimorphism, then if this x is projective, I want that its kernel here is projective as well. This will capture exactly this part. Any of these categories satisfy this, because here we have speech of the sequence, and x will be a byproduct of k and x, so x will be a retractable. And moreover, we have another class of trivial examples, which are the Schreier variety. Just variety when the three objects are just closed by subobjects are groups, are ring groups. Modules when R, the ring is principally like domain, or the algebra with K is a field. This is important because if you don't have K field, this fails. However, we have other examples of such categories satisfied this solution, which are not abelian and not Schreier. The first one was Lie algebra with K is a commutative ring. And we also prove that cross modules of a group satisfy the same condition, and more generally, just take a similar variety V satisfying itself the condition P. Okay, but what I want is I just wish that the D of Siena is projective, but I ask more than that, so maybe too strong for a condition. But no, it's very natural conditions in the sense that if I'm dealing with a logical category with binary coproduct, then condition P is equivalent to build that we call the Austrian lemma, which is like an additive version of the Austrian lemma that you maybe should know. Here we start with the projective resolution here, so take a sequence there, and then we can create here projective resolution here as well, and vertically we finish short text sequence as we end up in the well-known Austrian lemma. The Austrian lemma is crucial because for those who know, derived functors will lead to a long exact sequence homology. So this is a key result for linking to such result in non-abelian context. Okay, so I have my homotopy, I have suitable, it fits perfectly with homology, I have a condition to have that my homotopy behave well with projective resolution, so what should be my function now? We will just consider here quantitative functors, which was introduced by Thomas Senhardt and UCLouvain between pointed categories when just preserve kernel of epimorphism. But we should ask more than that. We should ask as well that those quantitative functors preserve binary coproduct, that they ensure that this collective between the subtraction hold as well. And finally, a condition that we need that such functor preserve proper morphism. This last assumption is not linked with my homotopy, it's linked with the homology in the non-abelian context. It was been proved by Thomas Senhardt, my supervisor, that if we expect that the homology take exactness in the non-abelian categories, we need to consider proper chain complex, which means that all the Dn are proper morphism, and then we recover that the homology vanish if only if the complex is exact at level An. In my situation, I'm starting with projective resolution, so it's exact. So it's proper, and then I wish that if I apply F, this remains proper in my codomain in E. Okay, so if I just combine everything, I have this result, which what I call the non-additive left derived functors. So just to sum up, I need C, the domain here as a polynomial category with binary coproducts in my projectives, satisfying my condition P. E should be normal, subtractive, and then I just use the functor that I just described before, and then I can just use the same formula as in my previous slide about the derived functors. Okay, obviously the strategy leads us to that all the examples that we know for derived functors fit perfectly, because the strategy that we use is just to enlarge the scope of derived functors. But we also have non-additive examples. The previous speaker talked about P0, so we'll not recall it, but here we can consider P0 from the cosmological groups, and then we ask ourselves if it was possible to do it for any semi-atomic category. Variety theory, that's the case, but we need that this variety satisfies P as well. And so, for instance, we can take V as the Lie algebra, but we can also iterate this construction. So we can have cross module of cross module of cross module and so on and so on. Okay. Should I have some? Yes. Okay. So I would like to shortly compare what I did before with the simple approach. Why? Because again, if you start with stability categories, then a simple method was also used to derive functors. And this was also a good equivalent way, because we have the total and Cook constants, which say that the simple objects are a simple category for the underlying category is equivalent to the positively chained complex over its abelian category. However, this is so important for abelian categories. If we move to semi-abelian categories, they're no longer equivalent, but we still have some good results. For instance, a couple of years ago, my supervisor and one of his collaborators proved that this following theorem, when you start with the semi-abelian category and you take two simple objects, if you assume that they are homotopically equivalent, and they're asymptotic, but in the simple way, then applying n, which is the normalization function, and then computing the emoji, we have the same thing. And this is not linked with the correspondence, so we don't have it. Okay. So that is the previous theorem. But what we prove is that we cover a part of John and co-equivalence correspondence, because this equivalence is not only for between the categories, it also ends up to these homotopy. And then here, if you start with the semi-abelian categories, and you have an homotopy between a simple object, then if you apply normalization, we end up with our homotopy that I described before. And then, if I apply the result that the homotopy behave well with the homology, we recover this thing what is proved before. Okay, but we can go further than that. Because, as I mentioned, we can use simple methods to compute derived functors. But what about my methods and the well-known methods in the literature? They're the same. Under which condition we need that C is homological now with binomial products in the projective, and this is that's my condition B, sorry. And C should be E should be semi-abelian category. Just consider the same functor as before, and then if you start with the simple resolution, or and just apply n, or starting with the chain projective resolution, then it will be the same thing. And the choice of F to be quadratic, we guarantee that this equality holds. And this is linked to the last part of the theorem mentioning that if C is a variety of algebra, then we can compare this result with the method of Bartek to construct simple resolution with a comonad. And so, yes, just briefly, my method and the simple one are the same. And I will conclude with this slide. Thank you for your attention. The strategy now is just to do with more abstract entropy or Quillen model theory and so on. And so, as you mentioned, another thing that we can do. So it's just the next step. And next time I hope to talk explore a lot, but not for the moment. Can you speak bit louder?
Is this enough to maybe compute something that is similar to X and
But X store is just based on functors which are additive or right exact or left exact. So here strategy was to build something that works and see if you have other examples. But I don't know. We should see. The only hope is that we have the non-exact in homology as this is the abelian context, and we have non-abelian assumption. So let's see if we still have some good talk, because we haven't yet computed those things for the P0. So let's see maybe something would happen here. Just don't know.
How does composition works with the left derived or right derived?
So you mean if you have two consecutive functors and
suppose you have two different functors which you can compose. Like a spectral sequence, the organic spectral sequence tells you how to compose functors, and then you can have derived functors of that, like derived functor of the composition f composition. Have you?
but
I mean, it's just a question. If you not say it's fine.
honestly, I don't know.
So basically, if you have two functors, which you can go, so you can talk about, say, left derived of a functor f. Then you can also talk about left derived of functor g. Suppose you can compose the functors f and g. Then spectral sequences, like particularly for organic spectral sequence, is a way where you can talk about the left derived of f compose g. How is it related to left derived of f and left derived of g? So that could be something nice to check with it.
But as you can see, our strategy is to look what is done in the real context and see what we can do, and so yes, I still need to read more. That's what I got here. But thanks for the comments.
Yeah.
question?
If something was not clear.